As we have mentioned before, reinforcement learning is a behavioral learning model. Reinforcement learning is different from supervised learning because the system is not trained with an already labeled dataset. Instead, the system learns through trial and error. In this essence, they look like the genetic algorithms. Reinforcement learning refers to goal-oriented algorithms, which learn how to attain a complex objective or how to maximize along a particular dimension over many steps. For example, they can maximize the points won in a game over many moves. RL algorithms can start from a blank slate, and under the right conditions, they can achieve superhuman performance. While neural networks are responsible for recent AI breakthroughs in problems like computer vision, machine translation, and time series prediction, with reinforcement learning algorithms, they can also combine to create something astounding like DeepMind's AlphaGo, an algorithm that beat the world champions of the Go board game. Reinforcement algorithms that incorporate deep neural networks can beat human experts playing numerous video games like StarCraft 2 and Dota 2. While that may sound trivial to non-gamers, it's a vast improvement over reinforcement learning's previous accomplishments, and the state of the art is progressing rapidly. Reinforcement learning solves the difficult problem of correlating immediate actions with the delayed returns they produce. Like humans, reinforcement learning algorithms sometimes have to wait a while to see the fruit of their decisions. They operate in a delayed return environment, where it can be difficult to understand which action leads to which outcome over many time steps. Take the example of the need to train a robot to navigate a set of stairs. The robot changes its approach to navigating the terrain based on the outcome of its actions. When the robot falls, the data is recalibrated so the steps are navigated differently, until the robot is trained by trial error to understand how to climb stairs. In other words, the robot learns based on a successful sequence of actions. The learning algorithm has to be able to discover an association between the goal of climbing stairs successfully without falling and the sequence of events that lead to that outcome. This diagram is commonly used to describe reinforcement learning. The agent is whatever taking the action. For example, a drone making a delivery, or Super Mario navigating a video game. The algorithm is the agent. If that's not clear, it may be helpful to consider that in life, the agent is you. A reinforcement learning agent interacts with its environment in discrete time steps. Action is the set of all possible moves the agent can make in these discrete time steps. An action is almost self-explanatory, but it should be noted that agents usually choose from a list of possible actions. When playing Snake, the list may contain going right or left, up or down. In the stock markets, the list may include buying, selling, or holding any one of an array of securities and their derivatives. When handling aerial drones, alternatives would include many different velocities and accelerations in 3D space. Environment is the world which the agent moves in and which responds to the agent. The environment takes the agent's current state and action as input and returns as output the agent's reward and its next state. If you are the agent, the environment could be the laws of physics and the rules of society that process your actions and determine the consequences of them. Reward is the feedback by which we measure the success or failure of an agent's action in a given state. For example, in a video game, when Mario touches a coin, he wins points. From any given state, an agent sends output in the form of actions to the environment, and the environment returns the agent's new state which resulted from acting on the previous state, as well as the rewards if there are any. Rewards can be immediate or delayed. They effectively evaluate the agent's action. This cycle goes on like this. Reinforcement learning is also the algorithm that is being used for self-driving cars. In many ways, training a self-driving car is incredibly complex because there are so many potential obstacles. If all the cars on the road were autonomous, trial and error would be easier to overcome. However, in the real world, human drivers can often be unpredictable. Even with this complex scenario, the algorithm can be optimized over time to find ways to adapt to the new state where actions are rewarded.